Section: Introduction. In this section, we discuss how reinforcement learning (RL) has gained traction as a method to improve the reasoning abilities of large language models (LLMs). This approach allows models to explore and refine their thought processes. Models like OpenAI's and DeepSeek show strong performance in reasoning tasks by learning to self-correct and think more analytically. These developments hint at early signs of metacognitive control, where models not only reason but also monitor and adjust their reasoning. However, LLMs still struggle with tasks that require precise numerical calculations or symbolic manipulation, such as geometric reasoning or solving complex equations. In contrast, computational tools like code interpreters (SIS) provide capabilities for symbolic computation that exceed what text-based reasoning can achieve. Unlike traditional reasoning methods that depend on language patterns, SIS offer a formal way to perform calculations, verify results, and reduce errors. Recent studies have looked into methods for training LLMs to use these tools, but these methods often fail to generalize beyond specific data patterns. This can lead to improper tool usage or reliance on weak strategies that don't work well across different problems. RL presents a solution by allowing models to explore flexible reasoning paths and learn how to use tools based on feedback from their outcomes. This approach encourages not just finding correct answers but also developing nuanced strategies, such as recovering from mistakes and deciding when to use tools during reasoning. In our work, we introduce ReTool, a framework that enhances LLM's reasoning by integrating external computational tools. ReTool has two main components. First, we create a high-quality dataset that teaches the model when and how to use the code interpreter, establishing a foundation for tool usage. Second, we apply tool-enhanced RL to help the model discover optimal strategies for using tools and adjust its behavior based on feedback, which goes beyond what supervised learning can achieve. During reasoning, the model can write code and get real-time results from a sandboxed code interpreter, aiding its thought process. We evaluate ReTool on challenging Math Olympiad benchmarks and find that our model significantly outperforms text-based RL baselines, achieving higher accuracy with fewer training steps. This shows that incorporating tool usage into the decision-making process not only enhances reasoning but also improves training efficiency. Additionally, our cold start model shows competitive performance, indicating that our dataset effectively captures tool usage patterns. We also analyze the cognitive behavior of the code interpreter during RL training and find that our model improves its ability to use code, select tools appropriately, and refine its reasoning through self-correction. In summary, we present ReTool, a novel RL framework that integrates code interpreter execution into LLM reasoning. We create a foundational dataset for tool invocation and design a framework that allows for interleaved code execution, enabling the model to optimize its reasoning strategies through feedback from the code interpreter. Our findings reveal significant improvements in reasoning efficiency and tool usage capabilities after RL training. Section Summary. In this section, we discuss the introduction of ReTool, a reinforcement learning framework that enhances large language models' reasoning by integrating code interpreter execution, allowing for improved tool usage and self-correction during complex reasoning tasks. Our approach demonstrates significant performance gains on Math Olympiad benchmarks, highlighting the effectiveness of combining RL with tool-augmented reasoning strategies. Section: Methodology. In this section, we introduce ReTool, a framework powered by continuous integration and reinforcement learning, aimed at solving math problems. We start with an overview of ReTool, followed by a discussion on our cold start training, which includes how we construct data and perform supervised fine-tuning. We then explain our reinforcement learning process, which is enhanced by a code interpreter sandbox to improve our model's strategic use of tools. Our methodology has two main stages: cold start supervised fine-tuning and reinforcement learning with integrated code execution. Initially, we gather data through our designed pipeline for supervised fine-tuning, which sets a strong foundation for the reinforcement learning phase. To improve our model's ability to use tools effectively, we implement a specialized reinforcement learning pipeline that helps the model choose and apply tools during reasoning. For our cold start, we created a pipeline to collect and curate high-quality data. We begin by sourcing existing mathematical reasoning data from various places, including open-source datasets like OpenThoughts. We then use a dual verification method that combines expert curation and automated evaluation to filter out invalid data. This process results in a high-quality dataset, which we call D_init. From D_init, we automatically create code-integrated reasoning data. We use a structured prompt template to transform the original reasoning process by replacing manual calculations with code snippets and their execution results. After this transformation, we verify the data in two stages. First, we check the format for readability and consistency, and second, we verify the answers to ensure they match the correct solutions. This results in a dataset, D_C, that includes code-augmented reasoning traces. We then use supervised fine-tuning to teach the model when and how to use the code interpreter, enhancing its ability to utilize computational tools. For our reinforcement learning, we train ReTool using the Proximal Policy Optimization (PPO) algorithm, which updates the policy based on specific objectives. During training, our policy model works with a code sandbox to generate rollouts that include real-time code execution for solving problems. We implement a rule-based reward system that allows the model to explore and develop strategies for using code effectively, including when to invoke it. To guide the model in learning how to use tools, we design an accuracy reward that evaluates the correctness of responses. We require the model to present final answers in a specific format for reliable verification. This reward system is designed to prevent reward hacking and encourage diverse problem-solving behaviors based solely on outcomes. We also propose a rollout approach that supports real-time code execution alongside natural language reasoning. Unlike traditional methods that only produce text-based reasoning, our approach combines text, code snippets, and real-time feedback from the interpreter. We use a prompt template to help the model interact with the code sandbox, marking code boundaries clearly. During the rollout, when the model generates text and detects a code termination trigger, it pauses, sends the code to the sandbox for execution, and receives feedback. This feedback, whether successful results or error messages, is integrated back into the model, allowing it to refine its reasoning and tool usage strategies iteratively. Section Summary. In this section, we introduce ReTool, a C-powered reinforcement learning framework for solving math problems, which consists of a cold start phase for supervised fine-tuning followed by a reinforcement learning phase that incorporates real-time code execution. We detail our data collection and verification processes, the training algorithm using PPO, and our innovative rollout approach that integrates natural language reasoning with executable code to enhance the model's tool utilization capabilities. Section: Training Details. In this section, we outline our training details, focusing on several key aspects. First, we implement an interpreter feedback mask, which prevents the feedback output from the interpreter from affecting our loss calculations. This method helps maintain training stability and protects the model's coherent reasoning sequences from being disrupted. Next, we address KV cache reuse. To save memory during rollouts, we cache all key value pairs before executing code whenever we detect a code termination trigger. We only calculate and add the KV cache from the interpreter feedback, significantly reducing memory usage for each rollout. We also construct a sandbox environment to speed up the reinforcement learning (RL) training process. The sandbox pods act as independent workers that pull tasks based on their capacity, creating an efficient load balancing system. This distributed approach allows for parallel interactions across multiple threads, preventing slower threads from causing delays and ensuring optimal resource use. In our experiments, we evaluate the performance of ReTool and analyze the model outputs. We use the VERL framework for training and adopt the Proximal Policy Optimization (PPO) method. Our hyperparameters include the Atom W optimizer with a starting learning rate of 1 millionth, a maximum sequence length of 16,384 tokens, a mini batch size of 512, and a KL coefficient of 0. We utilize the Qwen 2.5-32b instruct model as our backbone and repeat evaluations 32 times to ensure stable results, reporting the average accuracy for pass at 1. We compare ReTool against several competitive baselines and also against a text-based RL model to assess its effectiveness. Our main results show that ReTool allows the model to effectively use the code interpreter during the RL stage, leading to significant performance improvements. For instance, ReTool achieves scores of 67% and 49.3% on AMY 2024 and AMY 2025, respectively, with only 400 training steps, outperforming the text-based RL baseline, which scores lower with more training steps. This indicates that our tool-integrated learning approach not only enhances reasoning capabilities but also improves training efficiency. We also conduct a cognitive analysis, highlighting key findings such as the evolution of code interpreter behaviors during RL, the emergence of self-correcting abilities, and differences in code purpose before and after RL. We observe that the average response length decreases initially but then increases, indicating a shift to more efficient code usage. The ratio of responses containing code rises to nearly 98%, and the complexity of generated code increases significantly during training. Interestingly, we find that our model can self-correct non-executable code without explicit training for this task. For example, it recognizes missing imports and corrects them based on interpreter feedback, showcasing its metacognitive capabilities. We also analyze the purposes of code before and after RL training, noting a shift towards more diverse code purposes, which reflects improved adaptive tool selection. Finally, we compare C-powered reasoning with text-based reasoning, demonstrating that our approach is more efficient and accurate, allowing the model to focus on holistic reasoning rather than cumbersome calculations. Section Summary. In this section, we detail our training methodology for ReTool, which includes masking interpreter feedback to stabilize training, caching KV cache to reduce memory costs, and employing an asynchronous sandbox environment to enhance RL training efficiency. Our experiments demonstrate that ReTool significantly improves performance over traditional text-based RL methods, showcasing enhanced reasoning capabilities and efficient tool usage through comprehensive analysis of model outputs and behaviors during training. Section: LLM Reasoning. In this section, we discuss recent advancements in large language models, LLMs, that show progress toward cognitive abilities akin to human metacognition through chain of thought, COT, prompting. COT prompting enhances LLM reasoning by using step-by-step natural language descriptions, which significantly boosts performance on various reasoning tasks. Recent research has shifted from focusing on scaling during training to scaling during testing, where we allocate more computational resources during inference to generate intermediate reasoning steps. We utilize techniques like stepwise preference optimization, Monte Carlo tree search, and reinforcement learning to improve multi-step and long-form mathematical reasoning. Models such as OpenAI O1 and DeepSeek R1 demonstrate the effectiveness of COT-based reasoning. Additionally, we introduce program of thought, POT, reasoning, which incorporates external computational tools, like Python interpreters, to simplify and validate complex reasoning steps, leading to better accuracy. Tool-integrated reasoning was initially developed to assist LLMs in solving complex mathematical problems by combining programming strategies. We proposed an iterative approach that merges textual reasoning with code execution to enhance reasoning accuracy through mutual verification. More recently, we integrated code execution into the reasoning process by fine-tuning on self-curated COT data. However, this method is limited by its dependence on specific data distributions and lacks the ability to learn adaptive strategies for tool usage through reinforcement learning. Concurrent work applied reinforcement learning to learn tool usage strategies on Qwen 2.5 math models, but the results were not optimal. We expand on this research with ReTool, a framework that uses reinforcement learning to strategically decide when and how to use the code interpreter. Our method significantly outperforms Qwen Math 72 BTIR and O1 Preview on AMY 2024 and AMY 2025. We also provide a detailed analysis of the learned tool use behaviors and highlight important findings about the model's cognitive patterns in code invocation after ReTool training.